In today's video, we will learn what is displacement, the relationship between distance and displacement, and the difference between vector and scalar quantities. Let's jump right in. Let's start out by talking about what is displacement. Displacement is how far away an object has traveled from where it was initially located. We measure displacement by finding the difference between the initial position, where the object starts, and the final position, where the object ends. We can write this mathematically by saying displacement is equal to the final position minus the initial position. Now, in physics, we use the letters x, y, and z to represent the position of an object. We also use the Greek letter delta, which looks like a triangle, to represent the change in a measurement. Combining these ideas, we get displacement, which is delta x, the change in position. Again, it could be delta y if you're talking about vertical change. Final position, xf, we give it that subscript to let us know it's the final. Initial position, x naught, is usually how this is referred to, where you see that 0. The AP test and certain textbooks use x naught with a 0. Sometimes teachers and textbooks prefer xi to represent initial. Sometimes it's just personal preference. They both are good. And if we combine those statements together, the change in an object's position is equal to the final position, xf, minus its initial position, x naught. And there's our equation for displacement. Now, let's talk about why distance is different. Recall this formula that you see on the screen. This should look really familiar to you. It may have to jog your memory a couple years ago, but in middle school or in your intro algebra class like Math 1 or Algebra 1, you learned the distance formula, which measures the distance between 2 points on a graph, where you have x1, y1 and x2, y2. And then you threw it into this formula, and that told you the length between those 2 points on a graph. When we start out in physics, we focus on one dimension of motion. So we're just going to focus on x, or we're just going to focus on y. Therefore, we can simplify this distance formula to just include one dimension. In this case, oftentimes we start with x. So the distance is now equal to the square root of just the difference in the x positions squared. We can rewrite x2 minus x1 because it should look oddly familiar to you. It kind of looks like the formula for displacement. And in fact, you're right. We can go ahead and substitute in the displacement statement. So distance is equal to the square root of the displacement squared. Now here's the thing. The output is always going to become positive because whenever you square a term, even if our displacement was negative, a negative times a negative will give us a positive result. And because you are square rooting it, the only real solutions are going to be positive anyways. So we can rewrite the fact that it's going to always produce a positive output mathematically by using another old math friend, absolute value. And so our equation for distance is directly related back to displacement, except it's the absolute value of the displacement because it doesn't take into account the positive or negative sign. When we really start to line these two up side by side, they do have some things in common. In particular, sometimes students will get them confused because their unit of measurement is the same. Their SI unit is meters in both cases, which we use the letter m to represent. But displacement is a vector because displacement can be positive or negative based on the direction of motion. In this case, up and right are positive directions, just like you learned in math class, and down and left are negative directions. So depending on which way the object ends up moving, it may be a positive or negative displacement value. In comparison, distance has that absolute value, and because it has that square root of a squared value, it's always going to output a positive solution. Because really what distance is doing is it's measuring a length of the path traveled, and therefore it does not depend on direction. Now this might be your first exposure to the idea of vectors and scalars. However, you've been using them for years in your science classes without even knowing it. But in physics, it is really important that we define the difference between our measurements because it has a mathematical impact on our solution. A vector quantity includes both a magnitude, which is a numerical value, as well as a direction. So a magnitude would be something like 10 meters, 0 meters, while a direction is going to be signified in your calculations with a positive or negative sign. So it could be positive 10 meters, negative 10 meters. There's that extra component of a sign to represent what direction this measurement is taking place in. In comparison, a scalar quantity only has a magnitude. So just like what we talked about with distance, it's just going to have a number attached to it. Like when you grab a ruler or a meter stick, you're not naturally going to have any negative numbers located on it, right? It only gives you positive values from 0 to 100 centimeters. And in that case there, you would be working with something that's a magnitude because it'll give you a number, but you're never going to have to attach a negative sign to it because direction doesn't matter. You just flip the ruler to the direction you want it to be. So examples of vectors in physics are going to be things like displacement, velocity, acceleration, force, and many more, like momentum. While examples of scalars are going to be things like distance, speed, time, mass, and temperature. And we can get more into that as we go through the course. But hopefully that gives you a quick intro to the difference between a vector and a scalar quantity. Now let's get into some examples. In this case here, we have a runner begins their journey at the start line located at 0 meters and runs west 25 meters. Solve for the runner's displacement and solve for the runner's distance. Now, just there's a quick compass at the bottom of the screen in case you forget, but west is located to the left. Therefore, that is going to be a negative direction. North is up, so it's positive. East is right, so it's also positive. And south is down, so it is negative. So just keep that in mind when you see problems because physicists do like to switch back and forth between giving you left, right, up, down, giving you just signs, and also giving you compass directions. So it's good to practice them all. In this case here, we can see that they start at the start line, which is located at 0 meters, and travel west to the left 25 meters. So I set up a diagram here for us to label. First things first, I know that this is the start because they're going to travel west, which is to the left. I also know that my starting position is my initial position. And again, you can use xi or x naught, whatever your preference is. And in this case, that value is 0 meters. We then are going to travel west 25 meters. Therefore, my final position would be equal to 0 minus 25, which is negative 25 meters. This is where I end. Therefore, it's my final position. So when I go to calculate my displacement, first thing I'm going to do is write my equation. Displacement is equal to my final position minus my initial position. And in this case here, I would plug in my values. I have xi or x naught is equal to 0 meters and x final is equal to negative 25 meters. I'll plug it in. So we will get final minus initial, negative 25 meters minus 0 meters. And that's going to give me a solution of negative 25 meters as my displacement. So here's my first part right there. Now remember our equation for distance, we could write it as the absolute value of our displacement. So I'm going to take that number and plug it in. I know that my displacement is negative 25 meters. When I plug it into my equation, we're going to see that the absolute value of any number is going to output a positive result. So my distance is going to be positive 25 meters. And hopefully this lets you see The difference between something that is a vector value versus something that is a scalar value. We can see that there's a sign attached as well as a numerical value. And in the case of distance, there is just a numerical value. Let's try another example together. A kid rides their bike 15 meters east, then they turn around and travel 4 meters west. Okay, so thoughts? We have east, which is positive, we have west, which is negative. We're being asked to solve for the kids' total displacement and their total distance. I really want to highlight this because just like in regular math class or when you get a total for your bill, you're going to add all of the different components together to get your final answer, right? Just like you'd add all the prices on a bill to get your total. Now, in this case here, we're going to say that the kid starts at an initial position of 0 meters. They're going to travel 15 meters east. That's positive 15 meters. East is to the right. And at this point, they will end up at some position, we'll call it x1, which is 15 meters. This is our first part of this kid's journey, and that is their first displacement. Then they turn around and travel 4 meters west. So then they're going to go 4 meters west, which is to the left, which is a negative number. So that's going to be negative 4 meters. That is the second part of their displacement. And they're going to end up over here. Their final position is going to be 15 minus 4, which is 11 meters. Since we're solving for the total displacement, I would break this up into 3 parts. The first thing that we're going to do is solve for the displacement for the first path. Now, because they start at 0 and they travel 15 meters away, it's really nice and easy to calculate, but you can show your work mathematically to say the final position, which is x1 according to the diagram, minus the starting position, which is x initial, right? Now, in this case here, we could go ahead and plug that in, where this would be positive 15 meters minus 0 meters, and our displacement for the first part of the student's journey, just like is implied, is positive 15 meters. Could you just see that in the problem? You could. Can you prove it mathematically? You can. Now, step 2, we would go ahead and calculate the displacement for the second part of the path, where the final position is where the student ends minus the turning point, x1. Let's go ahead and calculate the displacement, which would be 11 meters minus 15 meters. Again, 11 minus 15 is going to produce a displacement of negative 4 meters. And our last step is going to be step 3, which is to get the total displacement. So that's going to be adding the 2 parts together. So we have our displacement from path 1 plus our displacement from path 2. In this case, our total is going to be equal to 15 meters plus negative 4 meters. So that's like minus 4 meters. And in this case here, our total displacement is going to be 15 minus 4, which is positive 11 meters. Again, the positive sign is completely optional, but what it lets me know is that the kid ends up riding their bike 11 meters east from where they started. Distance becomes really interesting in this case because remember that distance is a scalar value. It does not care about the direction that the kid traveled. And this is why it's actually important to look at those displacements separately, because distance, even for the total, is just going to be the sum of those 2 pieces. So it's going to be the sum of the first displacement plus the second displacement. But in this case, remember, we are only taking the positive solution because distance does not have a sign. So we can go ahead and plug in those two pieces to get our total distance is equal to the absolute value of 15 meters plus the absolute value of negative 4 meters. This is going to go ahead and simplify to 15 meters plus 4 meters. And 15 plus 4 meters is going to give us a total distance traveled of 19 meters. And that is our other answer. Which this type of problem really shows the power and the difference between distance and displacement, right? When you start looking at more complex paths that objects travel, you can see that there's a possibility for distance and displacement to not be the same answer. And that's because, again, distance only is taking into account the full length of the journey that's being traveled and does not care if you move back or forward, side to side, up or down. It does not care about direction at all. While displacement says, I care about how far away you end from where you start. And we can see here that the kid ends up riding their bike 11 meters east from where they started. However, they ended up traveling on their bike a total distance of 19 meters. I really hope that this video helped you have a better understanding of what is the difference between distance and displacement, what is a scalar and vector quantity, and how do we see this when we look at physics problems. I'll see you in the next video, and always remember that your growth will be found in the journey, not just in the solution. So get out there and go do some physics problems, and I'll see you next time.